Let's talk about 0/0 limits. So when we first get a limit where x is approaching a number and not one of the infinities, our first move is to always try to plug in the number to see if it has a y value, and we can use continuity to compute the limit. But there's a whole type of limit where when you try to plug in the number, you get 0 divided by 0. And this is a special type of limit that typically is indicating that there's a hole in the graph. So typically the limit does exist, but the 0/0 isn't enough information to actually get to the answer. We have to do one of these three tricks here. So if it's polynomial stuff, like these first few examples you see here, we're going to factor those polynomials, and we expect some of the terms to cancel. If you see fractions in the problem, like this last example here, then you're going to do the least common denominator, combine the fractions on top, and again, we expect something to cancel. And then finally, there's a third move called the conjugate trick if you have subtraction with a square root. This is a separate video. So in this video, we're just going to cover these two tricks. And again, conjugate trick is just a separate video. Okay, so let's dive into these examples to see these two strategies in action. So here we have the limit as x approaches 7 of all this. If we try to plug in 7, we'll have 7 squared minus 7 times 7, that's 0, same thing on the bottom. So we see the 0/0, and we suspect that this is going to be a hole in the graph. So we are going to factor the top and the bottom polynomials. So I keep the limit exactly the same. X squared minus 7x, I can pull out an x from each term, and I get x times x minus 7. And on the bottom, I can factor it into x minus 7, x plus 2. Minus 7 plus 2 are the numbers that multiply to -14, add to -5. And now it's not a coincidence that in this step, I have x minus 7 top and bottom, and that 7 is the limit number. So this confirms what I suspected, which was that 7 was a hole in the graph. And so I can cancel these terms, and without them, I can safely plug in 7. So we have x on top, so I'll plug in 7. And then on the bottom, just x plus 2, so I'll do 7 plus 2. Notice that in the step where I'm actually plugging a number in for x, so all the x's are gone, this is when the limit notation disappears as well, because this is me actually computing the limit. And we just add in the denominator, and we get our answer of 7/9. All right, let's try the next one. It's going to go a similar way. So here we have x approaching -4. So again, we try to plug it in. On the top here, we can see we'd have -4 squared is 16, and then plus a -16 here. Same thing on the bottom, so this comes out 0/0. So that indicates it's likely a hole in the graph. And because these are polynomials, we're going to take the same strategy as above, which is factor the top and bottom, and expect, in this case, an x plus 4 top and bottom to cancel. So I'll keep my limit the same, x approaching -4. In the numerator, it factors to x times x plus 4. In the denominator, there's actually more to do here. I can do it in one step or two. I'm actually going to take it in 2 steps. So 2x squared and 32 at least have a 2 in common. So I can pull that out. And then when I see the x squared minus 16, I see that that factors into x plus 4, x minus 4. If you don't remember that shortcut factor trick, what you could also do is just read this as x squared plus 0x minus 16 and factor it normally, and it brings you to the same place. So one more step to add in that factoring. Oh, wait, that wasn't an x, that was a 2. Okay, so this 2 is still here. And then x squared minus 16 becomes x plus 4, x minus 4. And sure enough, we can see the x plus 4 terms top and bottom. These are actually what's creating the 0/0 issue over here. It's always x minus whatever this number is, top and bottom. So we will cancel these guys. And as soon as they're canceled, we're safe to plug in -4 and actually compute a limit value. So on top, it's just an x, so that's a -4. On the bottom, I have 2 times x minus 4, so that's negative 4 minus 4. Right? So that becomes 2 times negative 8. And this computes to 1/4 as my final answer. All right, let's see the second strategy in action. So anytime we try to plug in our number and we get 0/0, we suspect it's a hole in the graph. So we're looking for cancellation. If it's polynomial stuff like these, we factor and cancel. And if you see fractions, you're going to make a least common denominator and combine your fractions. All right, so in this example here, again, our first step is to try to plug in 2 for x just to see if it'll compute. In the numerator here, we have a third minus a third, and in the denominator, it's 2 minus 2. So just like all the others, this is a 0/0 limit, and we have more to do to figure out what the number is going to be. All right, so I want to make a common denominator to combine the 2 fractions in this numerator here. That LCD is just going to be x plus 1 times 3. So this fraction needs a times 3 top and bottom. This one needs an x plus 1 top and bottom. And I'll combine them into a single fraction. Again, carrying over my limit notation. All right, so my numerator is now 3 minus 1 times x plus 1. You don't have to have this first 1 there, but it doesn't hurt. And then my denominator is 3 times x plus 1, or you could write it as x plus 1 times 3. It's all the same. And now what I'm going to do with the x minus 2, so I could write all of this over x minus 2, but then I would have like a triple-decker fraction, which my eyes really don't like. So instead of saying divided by x minus 2, I like to write it as times 1 over x minus 2. So it goes from the denominator to just a separate denominator. So this is equivalent, and it's, at least to me, a lot easier to look at. All right, so we need to clean up a little bit. There's not any obvious simplification that can happen just yet. So I'm going to start by distributing this minus 1 into the parentheses. So I have 3 minus x minus 1. And then in that numerator now, I have 3 minus x minus 1. The 3 and the minus 1 will combine to be 2 minus x. So all this becomes 2 minus x. And I'm just going to, because I'm running out of space, just going to write that into the same line. So if I'm trying to plug in 2, it's the x minus 2's that are stopping me. Like those are what's creating zeros. So I want this x minus 2 to cancel with this numerator. And you can see they're only off by a little bit, right? This is 2 minus x, this is x minus 2. So instead of seeing this as 2 minus x, I can actually factor out a negative 1. And that gives me negative 2 plus x, which is the same as x minus 2. So let's throw in an additional line here. So that's negative 1. So instead of negative 2 plus x, I'll write x minus 2 over the 3x plus 1 times the 1 over x minus 2 that's been there. And now I can see that they cancel each other, and a negative 1 is left over in the numerator. So as soon as I do that cancellation, it's just like the previous examples. That's what was holding me back. So now I can just plug in negative 2 for x, and this is when the limit notation disappears because I'm plugging in. So negative 1 up top, 3 times 2 plus 1 on the bottom. And that simplifies to negative 1 over 3 times 3. So negative 1/9 is my answer. All right, let's try one more that uses that same strategy. You can see my last example on the screen here. So again, our first move is typically to try to just plug in 6. And on the top, that would give us 2/5 minus 2/5. On the bottom, that would be 6 minus 6. So that 0/0 suggests it's probably a hole in the graph. I'm looking at fractions, so let's do a least common denominator and see if we can get a similar cancellation top and bottom. All right, so once again, my least common denominator is just the product of the two, so 5 times x minus 1. So this fraction needs an x minus 1 top and bottom. This one needs a times 5. And I'll combine very similar to that last example. Keep my limit notation, x is still approaching 6. Now the numerator of this combined fraction will be 2x minus 1 minus 2 times 5, which I'll keep that way for now. And then it's over the common denominator, so that's 5 times x minus 1, or alternatively x minus 1 times 5, both are correct. And then I'm going to move this x minus 6 the same way that I did up here with the x minus 2. So instead of having all of this over x minus 6, I'm going to pull it off to the side as a 1 over x minus 6 separately. So this accounts for this down here. All right, so same as before, I just want to clean up this numerator. I'm going to distribute the 2 into these parentheses and of course multiply 2 times 5 to 10. Okay. 2x minus 2 minus 10 is 2x minus 12 rather. And then I take a step back because all the expanding and simplifying is done. And I don't see x minus 6's canceling, right? If I'm trying to plug in 6, I want x minus 6's to cancel top and bottom. I have x minus 6 down here, but up here it's not quite showing. But if I factor out a 2, I would have 2 times x minus 6. So this numerator, I'm going to replace or rewrite as 2 times x minus 6. So that then it perfectly cancels with what's in the denominator. And as soon as I have that cancellation, it's safe to just plug that 6 in. So this is the step where the limit notation drops away. The numerator, all that's left is this 2. The denominator is 5 times 6 minus 1. So we have 2 over 5 times 5. We get 2 over 25 as our final answer.